another of Shannon's papers in the Bell System Technical Journal, this time in 1951, was one called Prediction and Entropy of Printed English. So he was trying to quantify the amount of information in a sequence of characters obeying the rules of natural language. And here's the start of the paper. He was interested in things like how uncertain are we about the next letter in a long body of text, given some knowledge of what has gone before. And that's important for a variety of reasons. One of the applications is in cryptography, the one that's just been talking about, because typically, or very often, not always, but very often, we might be wanting to encrypt text written in some natural language like English, and we want to keep any potential eavesdropper as uncertain as possible about what that message is. So we need to be able to quantify how much inherent uncertainty there is in language. And this is what he did in this paper, both through some theory and some experiments. He used entropy, which we've seen a few times already, to measure how uncertain we are about the next letter of text given some number of letters beforehand. And he used that to come up with some estimates of the entropy of English. He was also interested in other ways of determining the entropy of English. He looked at not just doing so from compiling statistics from large bodies of text, but he looked at ways of measuring the entropy based on the knowledge of the English language, say, that a native speaker has. So he conducted experiments, and here's an example. He had a text, the lines marked 1, in which, and the text here was hidden, and he would ask somebody to guess the next letter. So it may well be that you would guess that the first letter is T, and the next letter is H, and the next letter is E, and whenever the guess was correct, you write a dash. Whenever the guess is wrong, you give the person the next letter and you write what that is. And through sort of analysing this and quantifying it, you can come up with a quantitative measure of the entropy of English as embodied in that person's knowledge of the language. He conducted another similar experiment where now he's recording, again, there's the hidden text up the top, and in the lines marked 2 is recorded the number of guesses that are required for the reader to guess the next letter. Again, you can analyse this and get some idea of their competence in the language. Now, I'll skip this graph. This just illustrates some different approach, the result of his different approaches to measuring the entropy of English. But one thing I wanted to show you was the result of some experiments I did on students. That sounds terrible, doesn't it? Okay, so I used to teach cryptography. And one of the things Shannon did was to kind of reverse the experiments I was just described, to see, so the question is, if we have some model of English based on knowing some previous section of the text and then sort of measuring our uncertainty about what comes next, how good is such a model of English? And one way to measure that is how good it is at generating plausible English. So one experiment that Shannon described in his paper was to have a body of text, but to show somebody only the last 2 words, say, I mean, you could do it with 1 word or 3 words, but let's say the last 2 words, and ask them to suggest a word that comes next, a plausible word. And keep doing this with the same person. Now, I used to do this with my classes, and each person would get to contribute a new word. And in the 1990s, when I did this, for example, out came this text. Hello, madam, I smelled the food was good fun. Is nothing is certain. I am immediately to know this is. Which sort of doesn't make sense in a global way, but it's actually interesting. And Shannon observed this phenomenon that it typically makes sense over, in some cases, a range of about twice the length of the text that people were actually shown. So although in each case here, each word was chosen plausibly based on only the previous 2 words, we often find strings of 4 or 5 words that are indeed very plausible. So I know there's some of my old or former cryptography students in the audience here, and probably there's one or two of you who contributed one of these words. So what can come home lucky, it happened too quickly, for one day sun was not potato but. You could possibly discern the personality of the class from psychoanalyzing these texts. I guess this was a class, mentioned a potato there not long before lunch maybe. Actually, Paul's here. I think, Paul, you were in that class. Where are you? Yeah. Do you remember which word you contributed? Probably lucky, because that would suit. In 2003, the person who does not know when they come with me and you've thought. And we were doing the same experiment on you as you were coming in. I don't know if we're in a position yet to show you the results of that. So many of you, not all of you perhaps, but many of you were asked, given these two words, could you suggest something that comes next? And Kerry and Srinivas kindly helped out. So I suppose we're reading down the left-hand column and then down the right-hand column, are we?
Correct.
Kerry?
Sorry, I didn't know what we were doing when I was doing it.
Somehow potatoes came up again. I assure you that's entirely coincidental. So I'll have a go at reading this. Claude Shannon, that's very interesting that people picked those as the first two words. Very topical. Claude Shannon ate potatoes brute force is not a valid sentence of long-term memorisation of random facts are cruel. That's certainly true, but not small enough now. Later, I am the once upon a time parsley, sage, rosemary and potatoes are very tasty hot dog. I have a final. That's... Okay, so draw what conclusions you will about your collective personality and what's on your mind, but it's very interesting how people in this sort of subject seem to have a natural affinity to potatoes, which I think is a new scientific discovery that's come out of today, which we will rush into print somewhere. Thank you very much, Kerry, for organising that. And thank you all for being willing participants in this experiment. I just want to go straight to a paper not written by Shannon. In fact, Shannon didn't publish this work himself. A very good mathematician called Alfred Lehrman published a few papers where he presented a game which he had heard from Shannon, and he presented his solution to the game. So here's the game, and there's an example board where we have vertices or nodes connected in some fashion by edges or links between the nodes, and we have a start node and an end node which we'll distinguish in some way and call S and T, and we have two players, cut and join. And the aim of cut, or what cut does at each turn, is to cross out one of the edges, one of the links. And the aim of cut is to cut all paths from S to T so that S and T become completely disconnected. There is no surviving path between them. Opposing cut is join. What join does each turn is to thicken an edge and thereby render it impossible to be cut. Can't be crossed out then, and the aim is to make a path of thickened edges joining S to T. So let's see a game between these foes in action. In this particular case, join goes first. You could do it either way. You just agree beforehand who goes first. Join goes first and thickens that top left edge. Cut has decided to cut this edge. I don't know what you think join should do next. Somebody reckon, is that you, Matthew? You reckon bottom right? Yeah? This isn't such a good player. Join has done this, which allows cut to cut here, which means that cut wins this particular game. But as some of you noticed, that wasn't the best. That second move of join's wasn't the best move, and had join played better, join would have been able to win that particular game. So here's a very simple scenario for this game. It doesn't have to be on the graph shown before. Who wins this one? Whoever goes first. All right, who wins this one? Cut, good. Who wins this one? Join. So we've seen three types of games so far. Whoever goes first wins. Cut wins whether or not cut goes first or second. And join wins whether or not join goes first or second. What about this one? Cut, correct. What about this one? Join, I think so, yeah. What about this one? So work it out. I won't... given those three categories, there is, of course, one other category. There is whenever you come to a game which is kind of, has no ties, this game has no ties, that can be proved. Whenever you come to a game that has no ties and players take turns, there are 4 possibilities. There's one possibility we haven't encountered yet, and that is the possibility that the second player wins, whoever that is. And I'll leave it as a puzzle to you, particularly the many students we have from John Monash Science School, to either come up with a game, an instance of this game where the second player always wins, whoever that is, or to come up with a reason why that never happens. So you don't have to do it now, that's a homework, and I'll expect written solutions by Monday morning. Okay, so this particular game with the grid appeared commercially in 1960, invented by another famous mathematician, David Gale, under the name of Bridget, and I think we'll leave it there. Thank you very much.